You know, in system design, we often talk about data, but not all data is the same, is it? Some of it needs structure, it needs hierarchy. Today, we're going to dive deep into trees, not just as another data structure, but as the fundamental way we manage that hierarchy and balance. Let's get right into it.
This right here, this is the whole reason we're talking. Think about it. A grocery list, that's flat. Apples, bread, milk. The order doesn't really matter all that much, and the items don't have deep relationships with each other. But the real world, come on, it's almost never that simple.
Exactly. I mean, just look around. A company's org chart isn't just a list of names. It's a hierarchy. A family tree has generations, right? The folders on your computer have subfolders inside subfolders. You've got levels, you've got dependencies, and a really clear order. A simple list just completely falls apart when you try to model this stuff.
And that is the absolute core insight. When how things are related is more important than just what comes next in a line, sequence isn't enough. You need a structure that's actually built for hierarchy. You need trees.
So, okay, what exactly is a tree? Let's break down its fundamental structure.
On the surface, it sounds incredibly simple. You've got your nodes, that's the data, and you've got edges connecting them. But the real magic isn't the pieces themselves. It's the strict rules about how they connect. That's where all the power comes from.
And these aren't just some random rules. They are what make a tree so powerful. There's always one single starting point, the root. You can never get lost in a loop because there are no cycles. And, this is the big one, there is only one way to get from any node to any other node. That's not a bug, that's a feature. It guarantees predictability, which is absolutely essential for any system that has to reason about data in an orderly way.
And look, this isn't some abstract academic concept. You use trees all day, every day. Your computer's file system, it's basically one gigantic tree. Those indexes that make databases so blazing fast, yep, often built with trees. Even the layout of the app you're looking at right now is probably represented as a tree under the hood. They are literally everywhere.
All right, let's zoom in on one of the most famous types of trees, the binary search tree. It comes with an incredible promise of lightning-fast searches, but it also hides a really critical flaw, a peril that can bring an entire system grinding to a halt.
The rule is just beautiful in its simplicity. For any node you pick, everything in its left branch is smaller and everything in its right branch is larger. This one simple rule means you can find anything you're looking for incredibly quickly. At every single step, you get to throw away half of the remaining data.
This perfectly captures the two faces of a binary search tree. On one hand, you have the promise, a balanced tree. It's short and wide. Searches are logarithmic, which is just a fancy way of saying that even if you double the amount of data, it only takes one extra step to find something. It's ridiculously efficient. But then, there's the peril, an unbalanced tree. It becomes tall and skinny. And here, the performance just completely collapses. It's no better than searching through a plain old list.
And that's the danger. An unbalanced tree just loses all its magic and becomes this long, glorified list. And this isn't some rare theoretical edge case. It happens naturally if you insert data that's already sorted. The very structure that's designed to handle order can be completely broken by it. Kind of ironic, right?
So this raises a massive question for any engineer. If this super elegant structure has such a fatal flaw, how can we possibly rely on it for critical things like databases or file systems that have to be fast all the time, no excuses?
Well, the answer is we don't just cross our figures and hope for the best. We engineer for balance. We accept a small trade-off in order to get an ironclad performance guarantee.
And that's where these advanced structures come into play. You've probably heard the names AVL trees, red-black trees, B trees. These are the heavy-duty workhorses of real-world systems. They're all just variations of search trees, but with extra rules specifically designed to stop that worst-case scenario from ever happening.
Their secret weapon is something called a rotation. Basically, as you add new data, the tree is constantly checking its own shape. If it starts to get a little too tall and lopsided in one direction, it performs this clever little shuffle of its nodes to restore balance. It's a tiny bit more work on every insertion, but it guarantees the tree stays short, wide, and efficient.
And this, right here, is a fundamental lesson in engineering. In robust systems, you never, ever assume ideal conditions. You build mechanisms to enforce them. You trade a little bit of simplicity for an absolute guarantee of performance.
Okay, so let's zoom out again. Trees are amazing for ordered data. But what if all you care about is raw lookup speed? How do they stack up against another giant of data structures, the hash table? This table really lays it all out. For just finding one specific thing, a hash table is, on average, faster. It's what we call O of 1, or constant time. It doesn't matter if you have 10 items or 10 million, the lookup time is roughly the same. But it knows nothing about order. A tree is a bit slower on average, that's our O of log n, but it keeps everything sorted. And that lets you do powerful things like, give me all the users between age 20 and 30. That's a range query, and it's something a hash table simply cannot do. And just look at that worst case row. A tree is predictable, while a hash table, well, it can get risky.
So here's the bottom line. This is a deliberate design choice. When you pick a tree, you are consciously giving up a little bit of that raw average case speed. And in return, you get guaranteed structure, you get order, and you get predictability.
At the end of the day, the entire game, when you're working with trees, comes down to one thing and one thing only: managing their depth. A shallow, wide tree is a fast tree. A deep, skinny tree is a slow and dangerous one. All of that complex engineering around self-balancing, it's all just to keep the tree from getting too deep.
This really sums it all up, doesn't it? In a pure head-to-head race to find a single item, yeah, the hash table's probably going to win. But systems aren't just about pure speed. They're about reliability. They're about predictability. They're about trust.
And that's the question at the heart of so much of what we do in system design, right? When does trust beat speed? The answer is all around us. It's in our databases, it's in our file systems, it's anywhere that performance needs to be not just fast on a good day, but reliably fast every single time. It's about choosing predictability over raw and sometimes very brittle speed. That's a fundamental trade-off, and understanding it is absolutely key to building systems that actually last.